There are different theories about what creates magnetic polarity. One widely accepted theory is based on the direction in which the electrons within a material are spinning on their axis as they orbit the nucleus of an atom. The theory states that the action of the spinning electrons produces a magnetic field. In non-magnetic materials, there are roughly equal numbers of electrons spinning in opposite directions, and consequently, they neutralize each other's magnetic effect. In magnetic materials, there are more electrons spinning in one direction than in the other. This excess of spinning electrons creates the magnetic force. When a large number of these magnetized atoms group together with their magnetic fields aligned, they form domains, represented here by boxes in a grid. Each domain has its own north and south poles, which in an unmagnetized substance are randomly arranged. Only when the magnetic poles of the separate domains become aligned does the material as a whole become magnetized with a north and a south pole.
Perhaps you remember being warned that mishandling a magnet would cause it to lose its magnetic power.
For example, if a magnet is repeatedly dropped, or if heat is applied to the magnet, the domains will be jarred into a random arrangement, demagnetizing the metal. In demagnetized materials which no longer have any overall polarity, the domains are scattered at random.
Let's look at another important characteristic of magnetic fields.
The lines of force flow in a specific direction, forming complete loops. The lines of force are assumed to flow in one direction, from the north to the south pole outside the magnet, and then continue right on through the magnet from the south to the north pole.
Another characteristic is that magnetic lines of force always tend to form the smallest loop possible. Like stretched rubber bands, the lines of force always try to contract toward the surface of the magnet.
A final characteristic is that magnetic lines of force never intersect. The lines of force will always run parallel.
These are important characteristics of magnetic fields because they affect how alternating current is generated and utilized. Be sure to keep them in mind. Now let's see how magnetic fields interact first with each other and then with different materials.
You may have tried experimenting with two magnets and noticed how they would either attract or repel each other. This happens because their magnetic fields are interacting. This interaction is determined by the second characteristic of magnetic fields that you were shown, the specific direction of the lines of force. Remember that the lines of magnetic force are assumed to exit the North Pole and re-enter at the South Pole outside of the magnet, and pass from South Pole to North Pole within the magnet. Keeping this in mind, when like poles are placed near each other, the direction of the lines of force are in opposition, pushing away or repelling one another. Conversely, when unlike poles are brought in proximity, the lines of magnetic force extending out of the North Pole of one magnet coincide perfectly with those that are passing into the South Pole of the other magnet, drawing them together. When the magnets touch, the two fields join together and form one magnetic field. The lines do not intersect, but run parallel to each other.
To sum up, unlike poles attract and like poles repel. These two laws of polarity give magnets their usefulness. Now, let's see why magnets attract certain materials and not others. You've already seen how iron, in the form of filings, is attracted to a magnet. But why? Let's work with something larger in order to find out.
Watch what happens when this nail is positioned near the North Pole of the bar magnet under the paper and iron filings are sprinkled on top. Notice that the filings form a different pattern here, indicating that the shape of the magnetic field has been altered. This is because, as compared with air, the nail provides an easier path through which the magnetic lines of force can pass. The ability of a material to permit a magnetic field to be established within it is called permeability.
Reluctance, on the other hand, is a material's tendency to oppose the passage of a magnetic field. Notice that, for example, when the magnet is held at this distance, it has no effect on the filings. This is because air has a much greater reluctance rating than iron or steel. But watch what happens when a metal paperclip is added. Because the metal has a greater permeability than air, the magnetic lines of force become concentrated within the paperclip, thereby attracting the filings. The greater the permeability of a substance, the stronger the resulting magnetic field within it will be. The paperclip has become magnetized through a process known as magnetic induction. Because of this, the paperclip is capable of magnetically affecting the iron filings. If it were to remain attached to the magnet for a long enough period of time, the paperclip would eventually become magnetized itself. But without the magnet, there is no magnetic attraction because the magnetic field is not passing through the paperclip.
Stop the program and complete activity number 2. When finished, continue watching the program.